here we have another function here. W is a function of x, y, and z. And there's a constraint here that specifies the relation between those input variables, y, z, and x, or x, y, and z. So this is our constraint here. So depending on how we think about the constraint, W will change differently depending on which variables are independent and which one is dependent. Okay, so they ask us to find dW dx when y is independent. They also ask us to find dW dz when y is also independent. So in this first list, x and y are independent. Obviously x is independent because you're thinking about changing x and seeing how w changes. The fact that the y is here also means that y is one of the independent variables. Okay, so we go to take both sides. We start with our function here, x squared plus y squared plus z squared, and we take the partial both sides with respect to x. So the derivative of x is x squared with respect to x is 2x. Y is independent, so if you change x, this is just held constant, so that's derivative is 0. But because x and y are independent, this constraint would mean that if you change x, then z is going to have to change. So z actually is going to depend on x. So we get 2z times the rate of change of z with respect to x. Now we just have to find dz dx, which we can get from our constraint, because our constraint says y sine z plus z sine x equals 0. So if we're looking for dz dx. So let's take the derivative of both sides with respect to x. There's some z's in here, so that would allow us to solve for dz dx. So we take the derivative of this. We have a function. Let's see. Well, actually, y is independent when you change x, so this is just a constant. And then we get the derivative of the sine is the cosine, evaluated at the inside, times dz dx. And now we go take the derivative here, and we get dz dx, the derivative of the first, times the second plus the first times the derivative of the second. Just took the derivative of this with respect to x. Z was a function of x, so we had to use the product rule here. Y was not a function of x, so it just acted like a constant, so I didn't have to do the product rule. I just took the derivative of sine z and got cosine z dz dx. Okay, and then the derivative of 0 over here is 0. Two of these terms have a dz dx in them. One of them doesn't, so let's factor out the dz dx from the two that have it. So we get dz dx, y cosine z plus sine x equals negative z cosine x. So dz dx is equal to negative z cosine x divided by y cosine z plus sine x. Plus sine x. Okay, so I use the constraint, assuming that x and y are independent, to get dz dx, which I can now substitute in here. So we're going to get 2x. We have 2z times this, so that's going to make minus 2z squared cosine x all over y cosine z plus sine x. Nice. Okay, so that is the way that w changes with x when y is also independent. Okay, the next one says, how does w change with z when y is also independent? So we're going to take the derivative of w with respect to z, assuming that y is independent. If y is independent, then this constraint means that if you change z, you also change x. So we'll try this here. We have dw dz. Let's see. Since z and y are independent, let's see, that x is dependent, so we get 2x times the rate of change of x with respect to z. X does depend on z, that's why we get the dx dz. But y is independent, so that derivative is 0, and then the derivative of z squared with respect to z is 2z. Now we need to go and pick up whatever dx dz is so that we can substitute in, and we can use the constraint to do that. So here's our constraint. Y sine z plus z sine x equals 0. We want to figure out what is dx dz. This equation involves x, so let's take the derivative of both sides with respect to z. We're still assuming that y is also independent in this case, so we're looking at dw dz when y is independent. So if y is independent, we take the derivative with respect to z. This is just a constant, so we get y cosine z Now we go take the derivative of this. Since z is the variable we're taking the derivative with respect to, and x depends on z, this is a problem for the product rule. So we take the derivative of the first with respect to z, that's 1, times the second, plus the first, which is z, times the derivative of the second, which is cosine x dx dz, and we know that's equal to 0, because the derivative of this constant with respect to z is 0. Okay, so it looks like dx dz only shows up there, huh? So let's get the dx dz alone, so we can substitute back in. We get z cosine x dx dz. I'm moving all this stuff over to the other side, so minus y cosine z minus sine x. So let's see, then dx dz is equal to minus y cosine z minus sine x all over z cosine x. That can now be substituted in here, so that we have 2x, let's see, times this, so times minus y cosine z minus sine x, all of that over z cosine x plus 2z. So we've got our derivative of w with respect to z when y is also independent. I just realized I forgot to complete this problem. They told us to find these derivatives at this particular point, 0, 1, pi. So I need to substitute in each of these derivatives, I need to substitute in 0 for x, 1 for y, and pi for z. So if I substitute in 0 for x, I get 0 here. 0 for x gives me 1 here and 0 there. Substituting in 1 for y just makes that a 1. And then z is pi. The cosine of pi is negative 1. So we have negative 2 times pi squared, negative 2 pi squared, all over negative 1 times 1 would be negative 1. So the answer to this first one is that dw dx, when y is constant at this particular location, is equal to 2 pi squared. Okay, that finished off that one. Now let's do the same thing. Let's find dw dz when y is independent at this location. Let's see, we're saying x is 0. If x is 0, then that wipes out all of this, right? And let's just make sure we don't have something 0 downstairs. Let's see, z is pi, and the cosine of 0 is 1. So yeah, this is the first term is just 0, and then z is pi, so we get 2 pi for this derivative.